All right, in this video, we are going to talk about how to find roots or zeros of polynomials. So first of all, C is a solution for P of X equals 0 is one way to say that we have a 0 or root, or we could say X minus C is a factor of P of X, or we could say C is a 0 or root of P of X, and C of 0 is an x-intercept. Okay, and so something is a solution if it is a root, a 0, an x-intercept, or a solution. So these are all ways to talk about the x-intercepts. And so when we're talking about higher degree polynomials, every nth degree has n roots, okay? So like a quadratic is degree 2, it's going to have 2 roots. A degree 3 polynomial will have 3 roots. These roots, they could be complex, they could be real, or they could be multiplicities. Okay, and so a multiplicity just means you have a repeated factor. So a repeated factor. So for x squared plus 6x plus 9, that's a perfect square trinomial. It factors to x plus 3 times x plus 3. And so another way we could write that is x plus 3 quantity squared. And so that means x equals negative 3 is a 0 with multiplicity 2, because the factor x plus 3 is repeated. Okay, and so you may only see one unique x-intercept, but technically there's still 2 because you have one solution with a multiplicity of 2. Okay, and so how we find these is by factoring if we can. So that's why we had to talk about how to factor these higher degree polynomials. So starting with number 1, to factor this, I am noticing that my last term isn't constant, and so that means I'm going to have a GCF that includes the variable. And so every single one of these terms can be divided by x, and they can also be divided by 2. All these numbers are even. And then if the leading term is negative, so is your GCF, okay? Always factor out a negative if your leading term is negative. And so factoring out that negative 2x leaves us with 9x squared, divide the coefficients, subtract exponents, minus 6x, and then plus 1. Okay, and so now we have a quadratic to factor, and so we need 2 numbers that multiply to a times c, which is 9, but add to negative 6. Those numbers are negative 3 and negative 3, so I know I'm working with a perfect square trinomial. And so we have to split the middle with that. Minus 3x. Minus 3x plus 1. I can divide 3x out of the first pair, leaving me with 3x minus 1. I can get negative 1 out of the second pair, leaving me with 3x minus 1. And so one of my factors is 3x minus 1, and the other is 3x minus 1. Okay, and then don't forget about this GCF that we factored out from the very beginning. Okay, and so all of this is still equal to 0. And notice we were starting with a degree 3 polynomial, and so we're looking for 3 factors that will lead us to 3 solutions. Okay, and so my 3 factors is negative 2x, 3x minus 1, and 3x minus 1. That 3x minus 1 has a multiplicity of 2. And so when I set that factor equal to 0, I get 3x equals 1 or x equals 1/3. So 1/3 is one of my solutions, and he has a multiplicity of 2 since that was repeated twice. So I just put M2 to signify that it has a multiplicity of 2. And then we also have to set the negative 2x equal to 0, which would just lead us to x equals 0 as our third solution. And so it says solve, we just did that, and determine the number and type of roots. Okay, and so here technically we have 3 real rational. Rational means there's no square root in our answer. 3 real rational, and only 2 of them are unique because one has a multiplicity of 2. Okay, this next one I recognize as a sum of cubes. X and x cubed and 1 are both perfect cubes. And so you make one set of parentheses and then a larger set. You copy the sign, same, opposite, always positive. X is our A and 1 is our B. So A, B, A squared, B squared, AB. And so X, 1, X squared, 1. 1 times x is just 1x. Okay, and so these are our 2 factors. This quadratic is prime, so there's nothing else we can do with that. And so when I set the linear factor equal to 0, that's a quick, easy solve. We get x equals negative 1. To solve this quadratic, it's not factorable. And so you either have to complete the square or use the quadratic formula. I like the quadratic formula, especially when your b value is odd. Okay, and so in this case, A is 1, B is negative 1, and C, just identifying our A, B, and C values, not the same A as this. And then C is 1. So using our quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. And so negative b would be 1, b squared would be 1, minus 4 times a times c all over 2a would simplify to 1 plus or minus 1 minus 4 over 2, which is 1 plus or minus square root of negative 3 over 2. Square root of negative 3 is I root 3, and that is the best we can do to simplify. Okay, and so we have 3 solutions, which we would expect from a degree 3. 3 solutions. 1 real rational, and then 2 of them are complex. They have that I involved. Complex means I is involved. Okay, for this next example, we need it set to 0, just like our quadratic equations. And so it's best to have a positive leading term. So I am going to move x cubed over, and I'm going to move the 2x over. Okay, and so that gives me x to the 4th minus x cubed plus 2x squared, putting them in order, minus 2x equals 0. Once again, my last term is not constant, so I can divide out an x from each term, leaving me with x cubed minus x squared plus 2x minus 2. And then now I am seeing 4 terms, which signifies we should try to factor by grouping. So out of the first pair, I can factor out an x squared, leaving x minus 1. Out of the second pair, I can factor out a 2, leaving an x minus 1. So x minus 1 is one of my factors, x squared plus 2 is the other. Don't forget this GCF that we had. And so because we were factoring a degree 4 polynomial, we are looking for 4 solutions. I'm going to get 1 here, and 2 here. This x squared plus 2 is not factorable, and so we'll have to solve that a different way. So for this x, that would lead us to x equals 0. This x minus 1 would lead us to x equals 1. And then for x squared plus 2, when I set that equal to 0, since there's no x term, the best way to do that is to just subtract 2 from both sides and then use our square root property, which says x would be the positive or negative square root of negative 2. From there, we just need to simplify. That would be I root 2. Okay, and so 2 of my solutions are real and rational. In these two solutions, the positive and negative I root 2 are both imaginary, purely imaginary. There's no real part to them. Okay, for this last one, we need to move the x cubed, the 8x cubed to the other side, put it right in the middle. Once again, my last term is not constant, so we can divide out an x from each term, leaving us with x squared minus, x to the 4th. Subtract 1 from each exponent, minus 8x squared plus 16. And now I see 3 terms, and so we can try u substitution. I have a 2-to-1 ratio, and so if I let u equal x squared, this would be u squared minus 8u plus 16, which factors to u minus 4, u minus 4. And so when I put the x squared back, I have x squared minus 4, x squared minus 4. And both of those are difference of squares, x plus 2, x minus 2, x plus 2, x minus 2. Okay, and so if you wanted, you have 2x plus 2 factors, so you can write that as x plus 2 quantity squared. You have 2x minus 2 factors, you can write that as x minus 2 quantity squared. And then don't forget this x from the very beginning, that GCF comes back. We had a degree 5 polynomial, and so we have to have a degree 5 once we multiply it back out. Okay, and so we're looking for 5 solutions. Okay, so setting each factor equal to 0, I would have the x equals 0. I would have x plus 2 equals 0, which would lead to x equals negative 2. And then I would have x minus 2 equals 0, which would lead to x equals positive 2. This has a multiplicity of 2. And this has a multiplicity of 2. Okay, so all of my solutions are real and rational. So you can say 5 real, rational, but technically only 3 unique. Unique means they're not repeated. So 3 unique, rational, real, rational. I'll just put that in parentheses. Okay. The next part of this lesson is writing equations given the zeros. And so we have to remember something called the sum product rule, which if you are given the roots, you would add them together to get your b value, but you would take the opposite, and then you would multiply them together to get your c value. That's for quadratics. Okay, so the sum and product. So minus the sum for your x term, and then read that minus as opposite. Okay, that's only for the middle term. The product stays the same. The other thing you must remember is that if a plus bi is one of your roots, its conjugate, a minus bi, is also a root. Okay, and so this is helpful when you have imaginary roots. For this first one, we have 3 roots. So it says write a polynomial of least degree in standard form with integral meaning whole numbers. No fractions, coefficients that have the given zeros. So if my zeros are 6, -3, and -2, that means I'm going to have three factors, x minus 6, x plus 3, and x plus 2. Okay, and so we just need to multiply all of this out, 2 at a time. So for the first, we're going to FOIL and get x squared plus 3x minus 6x minus 18. That would give me x squared minus 3x when I combine my like terms, minus 18. Put that back in parentheses because we still have to multiply the x plus 2. Okay, since I do have 3 terms by 2, that's when I like to use the box. I'm going to put my 3 terms along the top. You can put them along the side if you would like. Okay, multiply coefficients, add exponents. That would give me x cubed minus 3x squared minus 18x, 2x squared minus 6x minus 36. Combining our like terms, we can combine 2 and -3 for the x squareds and -6 and -18 for the x. So that would give me x cubed minus x squared. And then -6 and -18 is -24, -36. So that would be our final answer. Standard form means multiply it out, no parentheses, highest exponent to lowest exponent. Okay, this next one is where our sum and product rule come into play. So I have two reals, 0 and -4. So I know x minus 0 would be a factor. I'm just going to write x. And then x plus 4 would be a factor. This other one is a complex root, which means his conjugate is also a root. Okay, and so that's where I'm going to want the sum and product rule. So I'm going to go ahead and multiply the first pair, x squared plus 4x. I'm going to leave that in parentheses because I'm also going to have to multiply it by this result. And so the sum of those the i's would cancel and leave me with 10. The product, we have to FOIL, and your i's should cancel. So 25 minus 5i plus 5i minus I squared. The i's cancel. I squared is the same as -1. And so that would become plus 1, so 26. So my quadratic would have x squared minus 10x plus 26. Okay, and so now I just need to multiply that purple quadratic by this red quadratic. So x squared 4x and then we would have x squared minus 10x plus 26. That would give me x to the 4th minus 10x cubed, 26x squared, 4x cubed, minus 40x squared, 80 plus 24, 104x. Combining some like terms, 4 and -10, and then -40 and 26. So that would give me x to the 4th minus 6x cubed minus 14x squared plus 104x for my final answer. So the least degree we could do is 4th degree. And that would be the standard form.